going to consider the delay, right? So basically, we are going to use this one infinite zeros. So in this question, if there is one time delay, so we are going to remove this one. Okay, you don't have this whole, sorry, you don't have these zeros, right? So basically, you only have this one. Then you do the gain matching, right? So basically, this is your gain. Okay. And for some of you are applying MATLAB, use some of the either control design, FYP, or your some other project. Okay, actually MATLAB, you also got certain command which you can directly use. Okay, to convert from continuous to your digital. So basically, your C to D, continuous to digital. And this type they use is called a match. So basically, this one is a match. Okay, the second method we are going to talk today is sample and hold. So about 2-3 weeks ago, we have discussed about the sampling and discussed about the holding, right? So if we look at the process of your sampling and holding, so first of all, you have your continuous input, right? You have your continuous input in your control, in your input control system. Your control system, what you have. Are you still able to figure out what is your raw diagram for your control? Yes or no? I hope the answer is yes. At least I hope 2 weeks later the answer is yes. Okay. So if you have your input from your sensor will measure what is your input, then you compute the error, right? So basically the error data EP is your input to your control block. And from the physics words, the velocity, the voltage, the current, all the things are continuous data, right? So you have your E with a small e. It means your data is continuous. After you obtain the continuous data about the movement, about the voltage, about the pressure, and so forth, then before you go to your computer will only look the value at certain sampling time. So we have sampler. So sampler is a place for you to convert your analog to digital, right? So after the sample, I get the sample data EK rather than E. So based on the EK now I have a digital input, I can do certain control operation. But if, let me see, we don't consider the control algorithm and movement. Anyway, after the control algorithm, what you get your digital output, right? We only look at the signal processing. Okay, my understanding for some of students is for mechatronics students, I think something very good for them. They are learning signal processing. Or signal system or something like that, right? So basically, I've learned something about the analog and digital conversion. So basically, the sample and hold method is actually the same. Okay? So after you get your digital data, if you do the holding, basically what you are doing, you convert your digital data into your analog data. After you get your analog data, you apply your transfer function, you apply transfer function, you get your analog output. After you get your analog output, you do the sampling again, what you get? Okay, let me repeat one more time. To help you to really understand what I mean. If we have a digital controller, if you have a digital controller, what is your input? Your input will be your EP. What will be your output? Your output will be a digital output, which is EP. Alright? If you have a digital controller. So if you have a digital controller, so basically you put your digital input to the digital controller, you get your digital output. So this is your so-called the digital controller. Right? So now if I want to find out the equivalence, so this means my digital controller can be equivalent to certain analog controller. If we do some digital to analog converting first. Then I get analog input. After I get the analog input, I look through the transfer function. And through the transfer function, I get my analog output. Then I do the same thing again. I get my digital output. Okay, please pay attention. This is something we need to learn. 2 weeks ago, when we introduced the sample and holding, so basically that one we do from the analog signal convert to digital signal. Then we have a digital transfer function. Then through the digital transfer function, we do the holding convert to analog signal as an analog output function. That one is from the point of view of the control. From point of view how we really implement digital control. Because digital control basically you will convert your analog input into a digital input, so your controller can compute. After your controller compute, you get your output. But digital output is not something to be really taken by the analog continuous plate. So you need to do the holding or you need to do the digital analog converting. Then you have your analog output. Then analog output can control your aircon, to control your motor, to control your engine, and so forth. That one is basically look at the control process. But today we are going to look at the equivalence. We are more looking into semantic equivalence to have certain equivalent control function to represent this process. Okay? So the difference is the previous one is more look for the practical control process. This one is more look into your semantic analog and digital equivalence. So in this case, it means, if let me see I have a digital control function which is x. What does it mean? If we find certain equivalent process, but actually it's not something we are doing. We never do such thing. We never have a digital input, then we do the holding first, convert into analog data, then you go to an analog controller, then you come out analog output, then you do the sample to become a digital output. We never done this in practical because it's meaningless. Correct? The reason for us to do a digital controller is because we have no choice, because we are using the digital computer. And also maybe because the digital signal conversion, digital signal transformation, more flexible, the more noise free, and so on and so forth, there's a certain advantage. But basically we are not so free. We get analog data, I convert to digital, digital convert to analog again. Then analog do the transform, then convert to digital again. We are not so free, we are so poor and nothing to do with analog to digital. No, we are not doing it. This one is just to see certain equivalence. Assume if you want to find out certain equivalent between your x and digital, what exactly is this x then will be your actual digital transfer function. It's something you really implement, as what we mentioned before. Alright? But now my challenge, my question, or some researchers they want to find out, what can be an equivalent transfer function? If we find an equivalent process. Because this one basically you have a digital input, you have a digital output. In practical, you just directly apply your digital controller, right? I don't believe you have a computer. Then inside your computer, you take the sample already, now you do the holding to convert your digital back to your analog again. We're not doing such funny things, right? And also we are not going to have some analog control in your digital computer to do the process, digital control of HS. Alright, we're not doing so, right? If we can do so, we just do analog control directly. We're not so stupid, not so free from your E3 cover to your EK, then cover your EK to your ET. No, we're not doing so. So bear in mind, this one is not something you are practicing. It's just something. In real practicing, we have your digital input, digital controller, digital output. I want to find out systematically, mathematically, what is the equivalence if we have a continuous function which is x. But in order to make the equivalence, I need to convert your digital to analog. I need to convert your analog to digital. Is it alright? So this one, your hold and sample, basically it's just to find out the equivalence between your analog and digital. Is it alright? It's not something you are really practicing. Very simple lah. Here you got your original analog input already. You don't want to convert to digital, then convert to analog. method is just to find out an equivalent, okay, for you to do certain study, okay. So because we find this approach, you do the whole thing, you do the transfer function, you do the sampling, should be equivalent to this. Then we are able to do something like you do the sampling, you do the whole thing, and this is some function you are very familiar. So this approach is the same as, because this is HS. Once you have done the whole thing, this is your 1 minus ST multiplied with your S. If you still remember. You still remember what we talked about 2 weeks ago about the sample holding and so on and so forth. Your holding itself is 1 minus e power st, right? Multiply with your HS. Correct? And if we do the Z transform of this one is your holding, you do the Z transform, you are taking the same thing, right? Correct. Of course, I took a short form. The full approach should be you do this, then you do the inverse Laplace transform. After you have done the inverse Laplace transform, you get your time domain function, then you do the Z transform. Okay, I just want to make the formula look simple, so I just put the Z transform here. Okay, but the actual process, if you do the inverse Laplace transform, then you get your time domain. Then based on the time domain, you get your discrete A function, then you do the Z transform. But through the table, it means you have the S function, but the S function you look the T function, small t. After you get small t, you get your K function. After you get a big K function, you get your K function. So I believe most of us, when you look at the table, basically you just look for S instead, right? But you need to understand that mathematically or in theory, you have this process. S mapped with the T. Reverse Laplace transform, right? T mapped with your KT sampling, right? Then for your KT to your Z. So basically it's your S function to your T function, and T function to a KT function, KT function to a Z function, right? Correct. This is how we look at the table, right? So basically the correct representation should be inverse Laplace transform on your HS to your HT. Then from your HT to your HAT sample, right? Then we do the Z transform, you get HK, right? Okay? But for most of the slides, we just make the screen clear. Okay, so sometimes I will just say Z transform. Okay? But theoretically, there is no direct transform from S to Z. It's your S to your T, T to AT, AT to Z. But when you look at people, it's very simple, right? You look at your suppose your Z people and your Laplace people, right? You have your S, you have your T, AT, and Z. So you just directly map your S and your T, right? Whereas this you were able to have that. But you should understand that it's a certain process. So after you have done this, what is your step transform of this one? So your E power SE basically is mapped as the one delay. Because this one we still need to map with integration, right? Because we use holding. Holding still about 1 over S because it's like integration. This one show you the different house, right? Because basically is 1 house minus 1 delay of a house. So this is something like your 1P, and this is your 1P with your 1P. Correct? So this is the reason eventually you get this one, right? So basically, for the children hope method, you have your continuous hs function, you divide by s. Then you multiply with your 1 minus s of this one. Okay, how this one has been defined, we have discussed 2 weeks ago, right? Now this one we will show you the so-called equivalence. And for the same case, the same low-pass filter. So what is the equivalence? If we are adopting the zero and four method, because your fs is a divided by s plus a. So what I need to do, first of all, I need to use hs divided by s. So I have a s plus a. So for this one, and you look at table directly, no, right? What you have to do? You have to do factorization. For the previous one, for the whole zero matching method, what you will need, besides this course, you need some mathematical tool which is called solve polynomial functions. And for this one, what you will need, some mathematical tool is to do the factorization, right? So for this one, this case is simple. Okay, if you don't know how to do, okay, a simple way is you take this one A minus this one B, right? Then you find the equivalence of your A and B. Okay? But to solve your I just solve already. Okay, this one. So after you get this, then what you get to do? Do the inverse Laplace transform, then sampling, then do the Z transform. But in practice, it's very simple. Look at the table, right? So in practice, what you're going to do? So from the table, your 1 over s is equivalent to so this basically on the table. Right? So this is basically you look on the table. After you get this one, you need to use so eventually you get this one. Okay, you will need to do some of the simplifications. Okay, the detailed process is not here. And the process basically is the same as you do the whole to do the sample and hold function as put together 2 ways ago. Okay. So basically the approach is use your hs divided by s. After you get this, look at the table to do the transform. Okay. After you get this one, multiply with 1 minus f of this one. Then you can get the equivalent Z transform function. And even that, you can use ZOH as a method to do the continuous polynomial. some option method. If you don't think zero order hole is a good enough, you can also try higher order. So for example, you can also do the first order hole. First order hole basically is to have a straight line to link your current point and your next. If you are doing zero order hole, what you are going to do? You hold this one here, hold this one here. That's slight different. So what I mean is, if we have a data, remember original data is something like this. At one point, think at one point here. If I'm doing the zero order hole, you hold. Zero is constant, right? Then I hold. I will get something like this. But if I'm doing the first order hole, and link this one to this one by a straight line, link this one to this one by a straight line, link this one to this one to a straight line, link this one to a straight line, this one to a straight line. When your sampling time is big, means when your sampling frequency is low, definitely you can see your first order will be much closer than your zero order hole, right? So this is very simple, like your zero hole, you just hold remain the same as the previous one, right? No contribution on it. But the first zero hole, at least you have considered your current and your next link together, right? And usually your current data and your next point will be suddenly jump. If you're doing the zero order hole, it's a sudden jump, right? But your first order is gradually linked, right? So if you look at the first order, then this is your center. You have two. Then you have this. So your basically you can consider this control function, okay, into one delay and second time delay. Then you get your z minus 1 squared divided by ez. And here your hs should be divided by s squared. You get a better result, but the process is slightly more complicated. Okay, this one won't be exam, okay, but just for some students, if you are doing some project, you want to consider first order approach. Okay, similar as your zero order approach. But you use the hs function divided by s squared. And you multiply with z minus 1 squared. So compare with your zero order hole, which only divide by s and only multiply with one order. Okay? For your first order, you have to do 2. So you can predict for second order, most likely you have to divide by s again, right? Okay, for student for interest, you can refer to the textbook. Okay, for more details. Before we do some practical exercise, okay, let's do a summary for what we have learned for all those elimination approach so far. So we have learned numeric integration. So we have forward, backward, trapezoidal, and we also have the trapezoidal. Sometimes we know the casting of all the bilinear transformation with free gradient. Right? So for the numeric method, we have 4. At least we have done 4 so far. Okay? And for 1, 2, 3, basically is you substitute the s. You replace s by certain approximation functions. Right? So this is something we have reviewed here. So these are the basic 3 numeric integration approximation. But we also understand even for this one, this is the closest compared with the other 2, right? So we still have certain distortion. So in order to compensate the distortion, then we have the so-called free gravity. We have the free gravity. Now we will do one exercise, okay, to show exactly how to do it. And today we have to use the zero and hole matching. So So basically, you find what are the zeros, what are the poles in your HS function. Then you just replace with e power st. So you get your digital pole, you get your digital zeros. If you get any zero at e finite in your S domain, you map with -1 in your budget domain. So this is a zero and pole matching. And lastly, we talk about the sector and pole. So that one, if you are taking the zero order pole, then we use your HS divided by S. Then look at the table, find out the Z function. Then multiply with 1 minus Z of 1. Okay? So these are the three methods. So let's do the example question together. And then you will have a better experience. Because just now, so far, most of the time we done is with ABCD, right? So to some of you, that ABCD is good, it's a general thing. Based on some of the student feedback, we prefer to do step by step, okay? Example first. So this question is taken from the textbook. So we have a fs function. So if you want to do some of the study of this one, okay. First of all, bear in mind, no matter which method we choose, because it is impossible to get exactly response compared with the continuous function, because there is always a distortion if your sampling time is not fast enough. Okay. So for this case, this one, we are going to do a network design to compensate a freeze angle about 60 degrees. And the frequency, the video frequency we are studying at is frequency at 3. So it's a 3 billion per second. So if we got a MATLAB, but basically, if you run the MATLAB command to calculate how much is the freeze angle, anyway, that's why you can also calculate the calculator, right? This is a transfer function. Then we are going to do the frequency analysis. If your frequency is 3, so how to use the frequency analysis? You replace your S by j omega, right? Still remember your lattice control? So you replace your S and your j omega, now your omega is 3. So if we do the analysis in your continuous domain, then this will be the complex number, right, of your h j omega, right? So for this one, if you run the MATLAB or you use your calculator to calculate how much is your freeze angle, and it's very simple, right? You use a calculator to calculate, right? Basically, you find out the angle of the complex number, right? So for this one, the complex number, the freeze angle is about 54.86. Okay. That's why we have to short down. So because we add this down, but we use this one as a reference. Okay, to see how much is the equivalence. Because basically we are supposed the equivalence, we want to find out the digital control achieve similar functionality as your original design analog controller, right? So if it's a Continuous or is an angle controller, you are supposed to get your freeze angle compensated by 54.86 or 87, okay, degree, okay, in angle of degree. So it's close to 60 degrees, not exactly 60, about 50.8658. So the first approach, we are going to use the forward. So for the forward is you are going to substitute your S with your Z minus 1 divided by T. So in this case, your H Z will become your Z minus 1 divided by T plus 1, 0.1 multiplied with your Z minus 1 divided by T plus 1, right? As simple as that. So original, this is your S, this is your S, and now you replace your S. Substitute your S by the Z function. And how much is your T? T is equal to 0.25, even, right? Then we can substitute the value A. It's up to you whether you prefer to substitute the value at the beginning, then everything you hear is a number. Or you prefer to convert to a general one and substitute your T with 0.25 up to you. So for this case, up and down, both multiply with T, so you get Z minus 1 plus T divided by 0.1 Z minus 1 plus T. So what you get eventually, Z minus 0.75 and 0.1 Z plus 0.15. Because your T is 0.25. So if you want to make all the coefficient for Z to be 1, then you can also multiply with N. So you get Z plus 1, right? This is what I get from the forward approach. Is this simple? Simple, right? Now we do the analysis. Is it stable? Stable? Why stable? What is the condition for the stability in your Z domain? All the poles must be inside the unit circle. So what is the pole now? So in this case, your zero of Z is 0.75. Your poles of your Z will be minus 1.5. And this one, your magnitude is greater than 1. It's outside the unit circle, right? So this one is unstable. But your original one, is it stable? Where's your zeros? It's minus 1. What is your poles? Is your minus N. This one is a negative value, right? It's stable, right? So you can see in your continuous domain, your HS function by right is supposed to be a stable function. But after you have done your forward approximation, it becomes unstable. So is this the result acceptable? Not acceptable, right? And if you want to do further, the further analysis, what is the freeze angle? You can use the calculator to find your freeze angle with your. Because now, if you want to evaluate the freeze angle, your Z is equivalent to E power ST, right? And now your frequency is 3, so it's 3J, right? At 0.25, right? So if you substitute this one into your Z function, you get your E power 3J is equal to n E power 3J. So it's 0.75 J, right? Because your T is 0.25. So So you have 0.75J, right? Then you minus 0.75 divided by 2 power 0.75J plus 1.5. So you can either use MATLAB or use your calculator doing that, then you will get the freeze angle, which is about 34.5. What is your original freeze angle? 4. It's only about 54.5. So basically this one, no matter you look at the stability, you look at the freeze angle, is something undecided. Okay? Even though we have done certain approach called over method, not guarantee this approach can give you a full result. We only tell you this is certain approximation. But sometimes this approximation may be good, sometimes the approximation